What if the key to turning lifeless planets into vibrant, Earth-like worlds isn't massive engineering projects or brute force, but something far more subtle, something invisible yet powerful enough to shape the destiny of entire worlds? Picture this, a barren, airless rock floating in the void, its surface scorched by radiation and frozen by the emptiness of space. Now, imagine awakening it to life, not with bulldozers or atmosphere factories, but with the quiet, relentless pull of magnetism. This isn't science fiction, it's a real possibility scientists are exploring right now, and it could change everything we know about our future among the stars. For centuries, humanity has dreamed of transforming dead planets into places we could call home. But the challenges are staggering. Without a protective atmosphere, cosmic rays and solar winds strip away any chance of survival. Without a magnetic field, even if we could somehow create an atmosphere, it would be torn away by the relentless forces of space. But what if the solution has been hiding in plain sight? Planetary magnetic fields, those invisible shields generated by the churning of molten metal deep within a planet's core, might hold the secret. These fields don't just deflect harmful radiation, they could also be the spark that ignites an atmosphere, creating the conditions for life to take hold. The idea is as elegant as it is revolutionary. By artificially generating or amplifying a planet's magnetic field, we might one day coax a thin, wispy atmosphere into growing thicker, trapping heat, shielding the surface, and setting the stage for oceans, clouds, and even forests. It's a vision that blends cutting-edge astrophysics with the timeless human drive to explore and adapt. And while the technology is still in its infancy, the implications are staggering. Imagine a future where Mars or even distant exoplanets could be cloaked in a protective magnetic embrace, their surfaces slowly blooming with the ingredients for life. This isn't just about survival, it's about rewriting the rules of what's possible in the cosmos. So, how close are we to making this a reality? Let's dive into the science, the challenges, and the breathtaking potential of terraforming through magnetism. The reason Mars stands as a barren wasteland today isn't just bad luck, it's a cautionary tale written in magnetism. Billions of years ago, the red planet once had rivers, lakes, and possibly even a thick atmosphere. But when its core cooled and its magnetic field faded, that protective shield vanished, leaving the atmosphere defenseless against the sun's relentless barrage of charged particles. Over time, solar winds stripped Mars bare, molecule by molecule, until it became the frozen desert we see today. This same fate could have awaited Earth if not for the swirling ocean of molten iron and nickel in our planet's core, which acts like a colossal dynamo, generating the magnetic field that cradles our atmosphere like an invisible force field. So how exactly does this planetary magnetism work? Picture Earth's core as a giant, spinning conductor. The movement of liquid metal generates electric currents, and those currents produce a magnetic field that stretches far into space, forming a protective bubble known as the magnetosphere. This bubble doesn't just deflect solar winds, it also traps particles, creating layers like the Van Allen belts that add extra shielding. Without this system, Earth's atmosphere would erode into space at a rate of hundreds of tons per day, leaving us as lifeless as Mars. But here's where things get fascinating for terraforming. If we could jumpstart or amplify a magnetic field around a dead world, we might recreate that protective embrace artificially. One proposed idea involves placing massive electromagnets in orbit around Mars, creating an artificial magnetosphere to shield the planet. Another approach looks at kickstarting the planet's core by injecting heat, or even using nuclear explosions to reignite convection currents, though that comes with its own set of risks. The goal is the same: to give a planet the armor it needs to hold onto an atmosphere long enough for natural processes or human intervention to thicken it into something habitable. This isn't just theoretical. Scientists have already modeled how even a modest magnetic field could slow atmospheric loss dramatically, buying us centuries or even millennia to nurture a stable climate. And while the engineering challenges are enormous, the payoff could be nothing short of revolutionary. A magnetic shield could turn Mars from a lifeless rock into a world where plants could grow, where skies could one day turn blue again. It's not magic, it's physics harnessed on a planetary scale. And if we succeed, it won't just change Mars, it'll change what we believe is possible for every dead world waiting among the stars. The story of Mars and Mercury isn't just about lost atmospheres, it's a warning written in the stars. These worlds weren't always the airless deserts we see today. Billions of years ago, they likely had skies thick with gases, maybe even oceans lapping at their shores. But without a magnetic field to shield them, those atmospheres were doomed. The Sun, with its constant stream of charged particles, acted like a cosmic sandblaster, slowly but surely stripping away their protective layers. This process, called atmospheric sputtering, is why so many rocky planets end up as lifeless husks. But here's the twist: if we understand how atmospheres are lost, we might just figure out how to bring them back. Think of a planet's magnetic field as an invisible umbrella, deflecting the worst of the Sun's fury. Earth has one thanks to its churning molten core, and that's why our atmosphere has stuck around for billions of years. But on worlds where that dynamo has shut down, the umbrella folds and the atmosphere vanishes. The numbers are staggering. Mars may have lost as much as 90% of its original atmosphere to sputtering. That's not just a slow leak, it's a catastrophic drain. And once it's gone, the planet's fate is sealed. No air means no pressure, no liquid water, no protection from radiation. It's a one-way ticket to desolation. So, how do we fight back? The answer lies in magnetism, either reviving a planet's natural field or building an artificial one. One idea involves placing gigantic superconducting coils in orbit around Mars, creating a magnetic shield strong enough to deflect solar winds. Another approach looks at jump-starting the planet's core, using targeted energy to get the molten metal moving again. There's even talk of using plasma superheated gas trapped in magnetic fields to simulate a natural magnetosphere. Each method has its challenges, but the principle is the same. Give the planet a shield, and the atmosphere might just regrow itself. The beauty of this idea is that we wouldn't have to build an entire atmosphere from scratch. Even a weak magnetic field could slow sputtering enough for natural processes like volcanic outgassing or comet impacts to replenish the air over time. Imagine Mars with a thin but stable atmosphere, just thick enough to trap heat and let liquid water pool in its valleys. From there, introducing hardy microbes or algae could kickstart a biosphere, turning the planet green one molecule at a time. It's a long game, but the payoff is a second chance for a dead world. And if it works, the same principles could apply to exoplanets light years away, turning the galaxy's graveyards into gardens. Of course, none of this is easy. The energy required to power an artificial magnetosphere is enormous, and tampering with a planet's core comes with risks we barely understand. But the alternative, leaving every airless world as a monument to cosmic indifference, is far less inspiring. This isn't just about survival, it's about stewardship. If we can harness the power of magnetism to heal a planet, we're not just terraformers, we're planetary doctors, mending wounds inflicted by time itself. And that's a future worth reaching for. One of the most promising ideas for creating an artificial magnetosphere involves superconducting coils, massive rings of wire, cooled to extreme temperatures where electricity flows without resistance. Picture a gigantic version of the magnets used in MRI machines, but scaled up to encircle an entire planet. These superconducting loops could generate a magnetic field strong enough to deflect solar winds, acting like a force field for Mars or other worlds. The concept isn't as far-fetched as it sounds. We already use superconductors in particle accelerators and experimental fusion reactors, where they create incredibly powerful magnetic fields in compact spaces. The real challenge is scaling this technology to planetary proportions, which would require breakthroughs in materials science and energy production. Another radical approach takes inspiration from nature itself. Instead of building physical coils, scientists have proposed injecting superheated plasma, a soup of charged particles, into a planet's magnetotail, the stretched-out portion of its magnetic field trailing away from the sun. This method would essentially turbocharge a weak or dormant field, using the same principles that create Earth's auroras. The process would involve launching satellites to release ionized gas at strategic points, creating a feedback loop that strengthens the planet's natural defenses. Early simulations suggest even a modest plasma injection could significantly reduce atmospheric loss, buying precious time for terraforming efforts. The key to making either of these ideas work lies in superconductors, materials that can carry immense electric currents without wasting energy as heat. Right now, the best superconductors we have require extreme cold, often near absolute zero, which poses a massive engineering hurdle in space. But researchers are racing to develop high-temperature superconductors that could operate in the frigid but more manageable environment of Mars or the Moon. If successful, these materials could revolutionize not just terraforming but space travel itself, enabling lightweight, ultra-efficient magnetic shields for ships and habitats. Of course, the energy demands for such projects are staggering. Powering a planet-sized electromagnet would require a reliable, massive energy source, likely advanced nuclear reactors or sprawling solar arrays in orbit. And then there's the question of stability. A magnetic field isn't a set-it-and-forget-it system. It would need constant monitoring and adjustment to counteract solar storms or fluctuations in the planet's core. But the potential rewards are worth the effort. With an artificial magnetosphere in place, a planet could hold onto its atmosphere for millennia, giving nature, or human ingenuity, the time needed to transform a dead world into a living one. What makes these concepts so compelling is that they don't rely on brute force methods like bombarding a planet with comets or flooding it with greenhouse gases. Instead, they work with the underlying physics of planetary protection, mimicking the processes that kept Earth habitable for billions of years. It's a subtle, almost elegant approach, one that could turn the galaxy's silent, airless rocks into future homes without rewriting the laws of nature. And while the technology isn't ready today, every experiment in fusion, every breakthrough in superconductors, brings us one step closer to making this vision a reality. The day we can weave magnetic shields around other worlds might be the day we truly become an interplanetary species. Superconductors could revolutionize how we think about planetary protection, acting like cosmic-scale electromagnets to cradle a world in an artificial magnetic embrace. These remarkable materials, when cooled to ultra-low temperatures, allow electricity to flow without any resistance, meaning they can generate incredibly strong magnetic fields without losing energy to heat. Imagine a network of massive superconducting rings encircling Mars, each one humming with currents powerful enough to deflect solar winds just like Earth's natural magnetosphere. The beauty of this approach is its elegance. Rather than fighting the laws of physics, we'd be working with them, using the same principles that have shielded our own planet for eons. Recent breakthroughs in high-temperature superconductors have made this vision less speculative. While traditional superconductors require cooling near absolute zero, a logistical nightmare in space, new materials can operate at slightly warmer temperatures, closer to the frigid but manageable conditions found on Mars or in shadowed lunar craters. Researchers are even exploring room temperature superconductors, though these remain elusive. Still, every incremental improvement brings us closer to the day when deploying superconducting coils around a planet becomes feasible. The key challenge lies in scaling up. We're talking about structures potentially thousands of kilometers in diameter, requiring materials and manufacturing techniques that don't yet exist. But let's say we overcome those hurdles. What happens next? A functioning artificial magnetosphere would do more than just deflect radiation. It could fundamentally alter a planet's relationship with its atmosphere. Solar winds, which normally strip away gases molecule by molecule, would be pushed aside, allowing any existing or introduced atmosphere to stabilize. Over time, even a thin shroud of gases could thicken, trapping heat through the greenhouse effect and creating a feedback loop where volcanic outgassing or sublimating ice adds to the air pressure. It's a slow process, but magnetism could provide the stability needed for nature or human intervention to do the rest. The real magic lies in the synergy between magnetic shielding and atmospheric chemistry. With solar winds neutralized, lightweight molecules like hydrogen and helium would no longer be the first to escape. Heavier gases, including carbon dioxide and nitrogen, could accumulate, forming the building blocks of a breathable atmosphere. Experiments on Earth with plasma confinement, like those in fusion reactors, hint at how these systems might behave at planetary scales. And while the energy requirements are colossal, concepts like orbiting solar arrays or compact nuclear reactors could supply the necessary power. Of course, there are risks. A malfunctioning superconducting loop could collapse the field, triggering rapid atmospheric loss. Solar storms, far more intense than anything Earth experiences, might overwhelm the system. And then there's the question of maintenance. How do you repair a planet-sized electromagnet in the harsh environment of space? These aren't trivial problems, but they're not insurmountable either. Every challenge invites innovation, from self-healing materials to autonomous maintenance drones. What's thrilling is that this isn't just theory. Scientists at NASA and private research groups have already modeled small-scale prototypes, testing how artificial fields interact with plasma streams mimicking solar winds. The results are promising, suggesting that even a partial shield could dramatically slow atmospheric erosion. And as our understanding of superconductors deepens, so does the potential to turn this vision into reality. We're not just talking about saving a planet's atmosphere, we're talking about rebirth. A world like Mars, given the right magnetic cradle, could one day wake from its frigid slumber, its skies gradually darkening with clouds, its valleys filling with whispers of wind. And if we can do it there, the galaxy's dead worlds might one day bloom. A restored magnetic field wouldn't just shield a planet, it would create the perfect conditions for an atmosphere to grow, molecule by molecule, like a cosmic greenhouse slowly filling with breathable air. Picture a world like Mars, its surface littered with frozen carbon dioxide and water ice. With a magnetic umbrella in place, solar winds would no longer scour away gases, allowing those trapped volatiles to sublimate into the air. Over centuries, the pressure would rise, temperatures would stabilize, and what was once a barren wasteland could begin to resemble the early Earth, where volcanoes belched nitrogen and methane into a sky thick with possibility. But where would these gases come from? The answer lies in a mix of natural reservoirs and human ingenuity. Every rocky planet holds pockets of volatile compounds locked in its crust: frozen carbon dioxide in polar caps, water ice beneath the surface, even nitrogen trapped in minerals. Heating the ground through targeted solar mirrors or geothermal drills could release these gases, mimicking the volcanic outgassing that built Earth's first atmosphere. Then there's the option of cosmic imports, redirecting water-rich comets or icy asteroids to collide with the planet, delivering not just gases but also precious water. These aren't wild fantasies, NASA. A Dawn mission already proved we can study and maneuver around small celestial bodies, and private ventures are eyeing asteroid mining. The raw materials for an atmosphere might already be within reach. The real magic happens when magnetism and gas sources work in tandem. A magnetic field doesn't just protect the atmosphere, it shapes its chemistry. On Earth, our magnetosphere prevents lightweight hydrogen from escaping into space, while heavier molecules like oxygen and nitrogen remain. Without that shield, Mars lost its lighter elements first, leaving behind a thin, carbon dioxide-dominated haze. But with an artificial field, we could tip the scales back in favor of stability. Imagine seeding Mars with cyanobacteria, organisms that thrive in extreme environments, converting carbon dioxide into oxygen. Under a magnetic shield, that oxygen wouldn't vanish into space, it would accumulate, molecule by molecule, until the air grew thick enough for liquid water to pool and plants to take root. Of course, balance is everything. Too weak a magnetic field and the atmosphere still leaks away. Too strong, and it could interfere with satellites or even alter weather patterns by trapping excessive radiation. Earth's field fluctuates naturally over millennia, but an artificial one would need fine-tuning, like adjusting the strength of an invisible force field to match the planet's needs. Early models suggest a field just 1% as strong as Earth's could dramatically slow atmospheric loss, buying us millennia to nurture the process. The parallels to Earth's history are striking. 4 billion years ago, our planet was a volatile place, its atmosphere a toxic mix of carbon dioxide and methane. Over time, geology and biology transformed it into the breathable air we know today. Terraforming through magnetism isn't about reinventing the wheel, it's about giving dead worlds the same chance Earth had, fast-forwarding their evolution with a little help from the fundamental forces of physics. And while the timeline stretches beyond a human lifetime, the payoff is a universe where lifeless rocks become frontiers, waiting for the first whispers of wind to stir their silent surfaces. Building an atmosphere from scratch means solving a cosmic supply chain problem. Where do we find enough nitrogen, oxygen, and carbon dioxide to blanket an entire planet? The answer might be floating in the darkness of space or buried beneath the very ground we're trying to transform. Take comets, for example. These ancient ice balls are essentially frozen time capsules, packed with water, carbon dioxide, and ammonia, a compound rich in nitrogen. Redirecting just a few dozen of them to collide with a target planet could release enough gas to kickstart an atmosphere. The math is staggering. A single mid-sized comet might carry billions of tons of volatiles, and while the impacts would be violent, they'd also be transformative. Imagine the spectacle: a string of cosmic snowballs plunging into a barren world, each impact vaporizing ice into steam and releasing trapped gases like opening a pressurized can. But celestial deliveries aren't the only option. Mars itself is a treasure trove of frozen gases, with polar caps containing enough carbon dioxide to triple its current atmosphere if fully released. Subsurface permafrost could hold even more water ice mixed with clathrates, cage-like structures trapping methane and other gases. Unlocking these reserves wouldn't require interstellar shipping. Instead, we could deploy drills or solar mirrors to heat the ground, coaxing the gases out slowly and deliberately. There's even potential in the rocks themselves. Certain minerals, like nitrates in Martian soil or carbonates in Venusian clouds, could be processed chemically to extract breathable nitrogen or carbon dioxide. It's like strip mining a planet's own geology to rebuild its sky. Each method comes with trade-offs. Comet impacts deliver bulk materials fast, but they're unpredictable. Too many at once could trigger global quakes or even strip away the fledgling atmosphere with the force of their explosions. Mining subsurface ices is more controlled, but it's energy-intensive, requiring vast networks of machinery operating in freezing, radiation-blasted wastelands. And chemical extraction, that's a slow, meticulous process like refining gold from seawater. The choice isn't just about efficiency, it's about philosophy. Do we take the fast, violent path of cosmic bombardment, or the patient, surgical approach of planetary alchemy? The real breakthrough will come when we combine these methods. Early stages might rely on comet strikes to inject raw materials quickly, followed by mining and chemical processing to fine-tune the mix. Over centuries, the atmosphere could evolve from a thin, toxic haze to something approaching balance, thick enough to shield against radiation but breathable for future colonists. And here's the kicker: once the first traces of gas accumulate, natural processes could amplify the effect. Warmer temperatures might thaw more ices, releasing gases in a self-sustaining cycle. Introduce hardy microbes to metabolize carbon dioxide, and suddenly you've got a biological engine helping to reshape the air. This isn't just about brute force engineering. It's about understanding how planets breathe, how they gain and lose gases over eons, and then nudging that system in our favor. The same forces that stripped Mars bare could, with the right interventions, help clothe it anew. And while the scale is daunting, the ingredients are already there, waiting in the ice and stone of dead worlds. All we have to do is learn how to wake them up. Creating a breathable atmosphere isn't just about quantity, it's about crafting the right chemical recipe on a planetary scale. Even with a magnetic shield in place, an atmosphere dominated by carbon dioxide or methane would be deadly to most Earth-like life. The challenge shifts from simply retaining gases to carefully orchestrating their ratios, like tuning a colossal atmospheric instrument. Earth's air didn't become breathable overnight. It took billions of years of biological and geological tinkering. Terraforming would need to compress that timeline dramatically while avoiding catastrophic imbalances. Take oxygen as an example. Too little and complex life suffocates. Too much and the entire planet becomes a tinderbox waiting for a spark. Earth's great oxygenation event 2.4 billion years ago shows just how disruptive this gas can be. It triggered mass extinctions of anaerobic life while paving the way for new evolutionary paths. On a terraformed world, we'd need to carefully regulate oxygen levels, possibly through genetically engineered algae or mechanical oxygen factories that adjust output based on atmospheric sensors. And that's just one component among dozens that require precise management. The thermostat challenge is equally complex. Greenhouse gases like carbon dioxide and water vapor trap heat, but their concentrations must walk a razor's edge. Mars today has plenty of CO2, enough to create a weak greenhouse effect, but not nearly enough pressure to sustain liquid water. Add too much and you risk runaway warming like Venus. Too little and the planet remains frozen. Proposed solutions range from orbital mirrors focusing sunlight onto polar ice caps to industrial-scale gas processors that extract or release specific gases, like dialing a planetary thermostat up or down. Biological approaches offer elegant solutions if we're patient. Introducing extremophile microbes could jumpstart atmospheric processing. converting CO2 into oxygen or locking away excess nitrogen. Scientists have already tested cyanobacteria in simulated Martian soil. With promising results, these hardy organisms survived and produced trace oxygen even in harsh conditions. Over centuries, entire ecosystems could be gradually introduced, each species playing a role in fine-tuning the atmosphere like instruments in an orchestra. The lichens that first colonized Earth's barren rocks, the plankton that fill our oceans, these could be the unsung heroes of planetary engineering. The parallels to Earth's climate systems are impossible to ignore. Our planet maintains balance through intricate feedback loops. Weathering rocks pull CO2 from the air, volcanoes replenish it, and life forms constantly exchange gases. Terraforming would require recreating these cycles artificially at first, then gradually handing control over to natural processes. Imagine synthetic weathering machines scattering mineral dust to absorb CO2, or floating algal blooms in newborn seas producing oxygen, each component working in concert under the protective umbrella of an artificial magnetosphere. What makes this balancing act possible is magnetism's hidden role in atmospheric chemistry. Beyond just shielding gases from solar winds, magnetic fields influence how molecules interact high in the atmosphere. Earth's field helps create the ozone layer, which blocks ultraviolet radiation that would otherwise break apart oxygen molecules. A restored magnetic field on Mars could enable similar protective layers to form, giving delicate atmospheric chemistry the stability it needs to mature. Without this invisible scaffolding, even the most carefully crafted atmosphere would unravel over time like a sandcastle against the tide. The ultimate goal isn't just survival, it's creating an environment where nature can take over. Just as early Earth's harsh conditions eventually gave rise to self-regulating systems, a terraformed world would need to reach that critical tipping point where atmosphere, climate, and biology maintain equilibrium. Magnetism provides the protective cradle, but the real magic happens when a planet begins to breathe on its own. When storms distribute heat evenly, when rainfall scrubs the air clean, when living things and their environment find that delicate balance we call home. That's when a dead world truly comes alive. A planet's magnetic field acts like an invisible conductor of climate, orchestrating everything from radiation levels to wind patterns in ways we're only beginning to understand. Earth's dynamo doesn't just deflect solar storms, it shapes jet streams, stabilizes atmospheric circulation, and even influences cloud formation through subtle interactions with charged particles. On a terraformed world, this magnetic influence could become the ultimate climate control dial. Imagine adjusting field strength to soften brutal temperature extremes or tilting magnetic poles to redirect weather systems toward arid regions, transforming global climates with the precision of a celestial thermostat. The science behind this is rooted in magnetohydrodynamics, how magnetic fields interact with electrically conductive fluids like Earth's molten core or an ionized upper atmosphere. When solar particles collide with a planet's magnetic shield, they don't just bounce off harmlessly, they create complex ripple effects. These interactions can heat the upper atmosphere, alter wind patterns, and even seed raindrops by influencing how charged water molecules cluster. On Mars, a restored magnetic field might initially create chaotic weather as new atmospheric layers form, but over decades, the system would self-organize into stable bands of circulation, like Earth's trade winds but tailored to Martian geography. Radiation management presents another fascinating opportunity. Cosmic rays that penetrate to ground level don't just endanger life, they also affect cloud nucleation and atmospheric chemistry. A carefully tuned artificial magnetosphere could filter these rays selectively, allowing enough through to maintain natural cloud cycles while blocking the most harmful bursts. This balancing act resembles how Earth's field naturally weakens during pole reversals, brief periods of increased radiation that may have driven evolutionary leaps. In our hands, such adjustments could become tools for guiding ecological development rather than leaving it to cosmic chance. The real breakthrough comes when magnetism intersects with greenhouse gas stabilization. On a world like Mars, where most CO2 exists as surface ice, magnetic protection could prevent newly released gases from being stripped away while simultaneously regulating their warming effects. Picture this: as polar ice sublimates under orbiting mirrors, the thickening atmosphere traps more heat, but an adjustable magnetic field modulates solar particle impacts to prevent runaway warming. It's climate engineering with two control knobs: gas composition and magnetic shielding, working in harmony to hit that Goldilocks zone of habitability. Yet these powers demand extraordinary responsibility. Tinkering with planetary scale systems could trigger unintended chain reactions, altering precipitation patterns that affect soil chemistry or creating new radiation hotspots near magnetic anomalies. Early models suggest even small artificial fields might disrupt delicate atmospheric equilibria in ways we can't yet predict. That's why proposals often include fail-safe configurations, distributed networks of smaller coils that can be adjusted independently rather than risking a single planetary scale experiment. What emerges is a vision where magnetism becomes the foundation for planetary stewardship, not just a shield against space, but a tool for nurturing fragile new climates into stability. The same forces that once protected Earth's primordial soup could one day cradle the first rains of a reborn world, guiding them toward balance one magnetic adjustment at a time. This leads us to an unavoidable question. Just because we can reshape worlds, does that mean we should? The ethics of terraforming force us to confront our role in the cosmos. Are we gardeners or conquerors? The answer may lie in recognizing that magnetism gives us not just power but perspective. A planetary field connects every living thing beneath it, reminding us that true transformation isn't about domination. It's about understanding the delicate dance between a world and its star and learning to step in rhythm. Before we can harness magnetism to reshape worlds, we must confront a question that transcends engineering. What gives humanity the right to remake a planet in our image? The ethical dilemmas of terraforming cut to the core of our relationship with the cosmos. On one hand, barren worlds like Mars appear lifeless, empty canvases begging for the brushstrokes of civilization. But what if we're not the first artists to touch them? Microbial life could still cling to subterranean aquifers or polar ice, remnants of ancient Martian biology. The moment we introduce Earth organisms or alter atmospheric chemistry, we risk obliterating alien life forms we don't yet understand, a cosmic version of colonizers trampling undiscovered ecosystems. This tension between expansion and preservation isn't hypothetical. Right now, spacecraft like NASA rovers undergo rigorous sterilization to prevent contaminating Mars with Earth microbes. Yet terraforming would require deliberately introducing organisms to process soil and air. It's the difference between tiptoeing through a museum and remodeling it with a bulldozer. Some scientists advocate for planetary parks keeping certain worlds pristine for study, while designating others for transformation. Others argue survival justifies action. If Earth becomes uninhabitable, shouldn't we secure humanity's future among the stars? The moral calculus grows even more complex when considering artificial magnetic fields. Unlike atmospheric changes which unfold over centuries, flipping a planet's electromagnetic switch could have instantaneous effects. A dormant world's chemistry might shift overnight as solar winds are suddenly deflected, exposing any potential native life to unfamiliar radiation levels or temperature swings. There's also the question of unintended consequences. Could jump-starting a magnetic field trigger seismic activity by altering currents in a planet's core? The same forces that protect could also destabilize, yet hesitation carries its own risks. Without intervention, planets like Mars will remain frozen tombs, their potential for life eternally locked away. Some philosophers frame terraforming as a moral duty. The universe has gifted us with intelligence, and with it comes the responsibility to nurture life wherever possible. They see dead worlds as orchards yet to be planted, and magnetism as the trellis that lets them grow. This perspective doesn't dismiss caution. It demands we proceed with reverence, transforming planets not as conquerors, but as gardeners tending the cosmos. The debate mirrors Earth's own environmental crossroads. Just as we grapple with reshaping our planet's climate, we now face those choices on an interstellar scale. But there's a crucial difference. Unlike Earth, Mars and other candidates for terraforming aren't yet balanced ecosystems. They're frozen in entropy, waiting for something or someone to tip the scales toward vitality. The answer may lie in a middle path where magnetic fields are deployed like adjustable scaffolding, creating protective zones rather than blanket transformations. Imagine cordoning off regions deemed scientifically precious while allowing controlled atmospheric experiments elsewhere, a compromise between conquest and conservation. What's clear is that magnetism alone won't resolve these ethical quandaries. Technology gives us the power to reshape worlds, but wisdom must guide how we wield it. The fields we generate around planets will one day ripple through history, marking the moment humanity chose either to impose its will indiscriminately or to become stewards of life in all its forms. And perhaps that's the ultimate test, not whether we can build planetary magnets, but whether we deserve to. Now, let's examine how these artificial fields measure up to nature's own designs. Earth's magnetic dynamo wasn't engineered. It emerged from the chaotic churn of molten metal. Can our human-made versions ever hope to match that elegance? The differences reveal surprising truths about what it really takes to cradle a living world. Earth's magnetic field is a marvel of natural engineering, a self-sustaining dynamo powered by the churning of molten iron in its core, running non-stop for billions of years without a single power outage. Compare that to even our most advanced artificial systems, which would need a constant, colossal energy supply just to keep a magnetic shield operational around a planet like Mars. The difference isn't just about scale, it's about resilience. A natural field can flex and ripple during solar storms, absorbing shocks like a cosmic shock absorber. An artificial one, it's more like a glass dome, powerful when intact but vulnerable to cracks if a single component fails. That's not to say artificial fields can't compete. What they lack in self-sufficiency, they make up for in precision. Earth's magnetic poles wander unpredictably, even flipping entirely every few 100,000 years, are hardly ideal for climate stability on a terraformed world. An engineered system could lock the field in place, optimizing protection where it's needed most. And while Earth's dynamo is stuck at one strength, we could dial an artificial field up or down like a thermostat, adjusting for solar activity or atmospheric growth. The trade-off is sheer energy demand. Powering a planetary scale electromagnet would require breakthroughs in fusion or space-based solar arrays, technologies still in their infancy. Then there's the question of durability. A natural field heals itself. Convection currents in Earth's core constantly regenerate the magnetic structure. Artificial coils, especially superconducting ones, are fragile by comparison. A micrometeoroid strike, a power surge, or even gradual material fatigue could cripple the system without redundant backups. Some designs propose distributed networks, thousands of smaller magnets working in concert, so the failure of one doesn't doom the entire shield. Others imagine self-repairing materials infused with nanotech, though that ventures into speculative territory. The real test comes during solar storms. Earth's field ripples but holds, channeling charged particles harmlessly toward the poles as auroras. An artificial field might falter under such stress unless engineered with room to flex. Simulations suggest hybrid approaches combining static orbital magnets with plasma injections that can swell defensively during solar flares, mimicking nature's adaptability. It's a reminder that while we can replicate magnetic effects, mastering their nuance takes more than brute force. These differences shape every terraforming strategy. Relying solely on artificial fields means committing to eternal maintenance, a civilization-scale project with no off switch. Some scientists propose kickstarting a planet's core instead, using targeted heat or kinetic impactors to revive its natural dynamo. It's riskier, but success could mean a self-sustaining shield for millennia. Others advocate for layered solutions, artificial fields as a temporary crutch while slower geological or biological processes work to awaken a planet's innate magnetism. What's clear is that magnetism isn't a one-size-fits-all tool. It's a spectrum of possibilities, each with strengths and sacrifices. And as we weigh them, we're really choosing between two futures, one where we perpetually tend to fragile shields, and another where we learn to coax planets back to life, letting them breathe on their own once more. Now consider how these fields interact with the very force they're designed to deflect: solar radiation. It's not just about blocking particles, it's about orchestrating a delicate dance between protection and transformation, where every deflection ripples through the atmosphere we're trying to nurture. The invisible shield of a planetary magnetic field does more than just hold an atmosphere in place. It acts as a cosmic umbrella, deflecting a relentless barrage of high-energy particles that would otherwise sterilize the surface. Solar winds and galactic cosmic rays, traveling at nearly the speed of light, carry enough energy to shred DNA and fry delicate electronics. Earth's magnetosphere absorbs or redirects most of this onslaught, funneling charged particles toward the poles where they ignite the auroras in harmless displays of light. But on a world without this protection, like Mars or the Moon, radiation doses at the surface could exceed astronaut safety limits in just days, turning long-term colonization into a game of Russian roulette with every solar flare. Artificial magnetic shielding wouldn't just be a luxury, it'd be a lifeline. Picture a future Mars base where colonists could work outside without cowering beneath meters of regolith or lead-lined habitats. Crops could grow in open-air greenhouses instead of radiation-shielded bunkers, and crucially, the microchips powering life support systems wouldn't succumb to constant glitches caused by particle strikes. A phenomenon called single event upsets that already plagues satellites in Earth's orbit. The difference between a shielded and unshielded world isn't just about safety, it's about feasibility. Without magnetism, off-world settlements might forever remain cramped, underground bunkers rather than thriving surface civilizations. But replicating nature's radiation defenses is easier said than done. Earth's field extends tens of thousands of kilometers into space, creating a vast buffer zone where harmful particles are gradually slowed and deflected. Building an artificial equivalent would require generating magnetic bubbles of similar scale. Think colossal superconducting rings in orbit, each one pulsating with currents strong enough to bend the paths of protons moving at relativistic speeds. The sheer energy needed to maintain such fields is staggering. For context, powering even a localized magnetic shield around a small Martian habitat would demand more electricity than a nuclear submarine reactor produces. Scaling that up to envelop an entire planet, That's territory reserved for fusion reactors or space-based solar arrays the size of cities. The challenges don't stop at energy. Magnetic fields interact with radiation in complex ways. Too weak and high-energy particles slip through like bullets through tissue paper. Too strong, and the field itself could become a radiation trap, creating zones where deflected particles accumulate into dangerous hotspots, a problem astronauts already encounter in Earth's Van Allen belts. Finding the Goldilocks zone requires precision engineering, possibly involving dynamic systems that adjust field strength in real time as solar weather changes. Some proposals suggest multi-layered approaches, a planetary-scale mini-magnetosphere to blunt the worst radiation, supplemented by localized shields over settlements for added protection. Radiation shielding also highlights a philosophical divide in terraforming strategy. Should we focus on protecting entire planets or prioritize smaller, oasis zones where fields are concentrated over habitable areas? The first approach mirrors Earth's natural design but demands Herculean resources. The second is more pragmatic. Imagine domed cities under magnetic umbrellas, with the hostile wilds left untouched, but risks creating planetary-scale gated communities where humanity clings to tiny islands of safety. What's often overlooked is how magnetism shapes more than just physical safety. Earth's field subtly influences biological rhythms, from bird migration to the navigation of bacteria. While we don't yet know if human health depends on these weak magnetic cues, long-term colonists on a world with artificial fields might face unforeseen adaptations. Could altering a planet's electromagnetic environment affect circadian rhythms or even neural function? It's a reminder that terraforming isn't just engineering. It's rewriting an entire planetary context where every change ripples through ecosystems we've barely begun to understand. The promise, though, outweighs the unknowns. A world with restored magnetic shielding wouldn't just be habitable, it'd be alive in ways barren planets can't match. Auroras would dance over polar ice caps again. Weather systems no longer bombarded by ionizing radiation might stabilize into predictable patterns. And beneath that invisible shield, the first shoots of greenery could push through alien soil without being crisped by solar storms. Magnetism isn't just a technical solution. It's the difference between surviving on a dead world and truly bringing it back to life. Powering a planetary magnetic shield isn't just an engineering challenge. It's a cosmic-scale energy puzzle where the numbers defy imagination. To sustain an artificial magnetosphere around Mars, estimates suggest we'd need continuous power output equivalent to hundreds of modern nuclear reactors working in perfect harmony. That's enough electricity to illuminate every city on Earth 10 times over, channeled into superconducting coils spanning thousands of kilometers in orbit. The sheer scale pushes against the boundaries of known physics, forcing us to reconsider what's possible when humanity's ambitions stretch beyond a single world. Fusion reactors emerge as the most promising solution. The same star-making process that lights our sun could one day energize planetary magnetic fields. Compact fusion prototypes like tokamaks and stellarators are already achieving brief plasma containment on Earth, hinting at a future where clean, virtually limitless power becomes reality. But even optimists admit commercial fusion remains decades away. Until then, alternatives like space-based solar arrays could bridge the gap. Imagine vast orbital farms of photovoltaic panels, each kilometers across, soaking up unfiltered sunlight and beaming energy via microwaves to receivers on the surface or at magnetic coil stations. The technology exists today. Japan's space agency demonstrated wireless power transmission over short distances as early as 2015, but scaling it to terraforming demands would require manufacturing capabilities rivaling entire planetary industries. Geothermal energy presents a darker horse candidate, especially for worlds like Mars with residual volcanic heat. Deep drilling could tap subterranean reservoirs, using the planet's own warmth to power surface-based magnetic generators. The approach has elegance, using a world's dying embers to reignite its protective shield, but faces daunting hurdles. Martian core temperatures may have cooled too much for practical extraction, and drilling tens of kilometers through alien crust makes Earth's deepest oil rigs look like backyard shovel projects. Distribution poses another nightmare. Unlike Earth's grid with its sprawling power lines, a terraforming energy network would need to operate across airless wastelands and orbital space. Superconducting cables could help, but maintaining them near absolute zero in the vacuum of space demands radical cooling systems. Wireless power transfer avoids physical connections but suffers from efficiency losses over distance. Every percentage point wasted means thousands of megawatts vanishing into the void. The solution might lie in decentralization. Thousands of small power nodes, each supporting a segment of the magnetic field, creating redundancy against inevitable failures. Historical parallels offer sobering perspective. The Apollo program consumed nearly 5% of the US federal budget at its peak, a moonshot effort requiring national mobilization. Building planetary magnets would dwarf that commitment, potentially demanding global cooperation spanning generations. Yet history also shows how energy needs drive innovation. The 20th century's electrical grid seemed impossible until alternating current made continent-spanning transmission routine. Perhaps fusion breakthroughs or exotic physics like zero-point energy will emerge from this very challenge, proving necessity remains the mother of invention, even when the necessity is rewriting a planet's destiny. Efficiency becomes the ultimate arbiter. Every joule saved in superconducting design or power transmission means less infrastructure to build and maintain. That's why researchers obsess over details like cryogenic cooling methods and room temperature. Superconductors' marginal gains compound into game-changing advantages at planetary scales. The difference between 95 and 96% efficiency could mean eliminating an entire fleet of orbital power stations. What becomes clear is that magnetic terraforming isn't a single invention waiting to happen. It's a symphony of technologies needing perfect synchronization. Power generation, distribution, storage, and conversion must all leap forward simultaneously, each advancement pulling the others into feasibility. The energy requirements might seem insurmountable today, but so did lunar landings before rockets left the atmosphere. Humanity's greatest projects have always begun as impossible dreams until they weren't. Turning our gaze backward reveals how often civilizations underestimated their capacity to harness energy. 19th century Londoners feared streets would drown in horse manure before automobiles arrived. Early power companies doubted alternating current could safely cross cities. The lesson: today's energy ceilings often become tomorrow's basements. If we can crack fusion, master superconductors, and build in space at scale, then wrapping worlds in magnetic shields shifts from fantasy to frontier, 1 megawatt at a time. This brings us to a pivotal question rooted in history. When have humans last attempted planetary scale engineering, and what can those efforts teach us about reshaping worlds? The answers might surprise you. Not all grand experiments unfolded in space. Some happened right here on Earth, with consequences both cautionary and inspiring. History shows that humanity has never shied away from reshaping environments to suit our needs. We've just never done it on a planetary scale before. Take cloud seeding, where aircraft spray silver iodide or salt particles into the air to coax rain from stubborn clouds. It's been practiced since the 1940s with mixed results, yet it proves we can tweak atmospheric processes deliberately, or consider carbon capture technologies, massive facilities that scrub CO2 from the air like artificial trees, still in their infancy, but already demonstrating we can manipulate global chemistry molecule by molecule. These projects pale in comparison to terraforming Mars, yet they share a common thread: the audacity to re-engineer nature itself. The parallels run deeper than ambition. Cloud seeding teaches us about unintended consequences, how inducing rain in one region might starve ecosystems downwind. Carbon capture reveals the staggering energy costs of planetary-scale tinkering, with current facilities consuming as much power as small towns just to filter fractions of atmospheric gases. These lessons loom large for magnetic terraforming. A miscalibrated field might deflect solar winds only to create radiation hotspots elsewhere, just as poorly planned cloud seeding once triggered floods instead of gentle showers. The takeaway: planetary engineering demands humility. Every intervention ripples through systems we barely understand. But history also offers hope. Look at the ozone hole crisis of the 1980s. When scientists discovered chlorofluorocarbons were eating through Earth's protective ozone layer, global bans reversed the damage within decades. It proved humanity could collectively alter and repair planetary-scale systems when motivated. Magnetic terraforming would require similar coordination, except instead of phasing out aerosol cans, we'd be orchestrating fleets of fusion-powered satellites to weave protective fields around worlds. The timeline for such projects stretches generations. Early stages like placing prototype magnetic coils in Mars orbit could begin within 50 years if fusion power advances as projected. Middle phases, where atmospheric thickening becomes measurable, might unfold over centuries, slower than continental drift but faster than Earth's natural climate cycles. The end point, a stable, self-sustaining biosphere, could take millennia, requiring patience beyond any civilization's recorded history. Yet seen another way, that's precisely what makes terraforming unique. It's not just a project for one era, but a legacy woven across lifetimes, each generation inheriting the work of the last, like stonemasons building a cathedral they'll never see completed. What makes this timeline plausible is how neatly it aligns with other cosmic ambitions. Lunar bases planned for the 2030s could test small-scale atmospheric containment. Martian colonies of the 2100s might refine local magnetic umbrellas over habitats. Each step builds toward planetary-scale interventions, just as medieval windmills paved the way for modern power grids. The key is recognizing that terraforming isn't a single thunderclap of transformation. It's the accumulation of countless small acts of engineering, each one bending the arc of a world's destiny toward life. The greatest lesson from Earth's geoengineering experiments isn't technical, it's philosophical. We've learned that no intervention is neutral, that every tweak to natural systems carries debts and dividends across space and time. Magnetic terraforming magnifies these stakes exponentially. A field adjusted too strongly might inadvertently cool Mars into a deeper ice age. Too weak, and nascent atmospheres bleed into space. But if history teaches anything, it's that humanity's boldest leaps begin not with certainty, but with the courage to try, and the wisdom to adapt when the universe pushes back. Transforming a dead planet into a living world isn't a sprint, it's a marathon spanning generations, a slow unfurling of possibilities measured not in years but in centuries. The first phase would be all about infrastructure, deploying orbital superconducting coils or plasma injectors to create that initial magnetic shield, a fragile bubble of protection against solar winds. This alone could take decades of precision engineering, with autonomous construction drones assembling megastructures in the void while scientists on Earth and Mars' fine-tuned field strengths in real time. Imagine the tension in mission control as the first artificial auroras flicker to life over Martian poles, proof that the shield holds, that the planet is no longer bleeding its atmosphere into space. But a magnetic field is just the opening act. Next comes atmospheric seeding, a painstaking process where frozen CO2 is coaxed from polar caps. Comets are nudged into strategic impacts, and underground permafrost is melted to release trapped gases. Early models suggest it could take 200 years just to reach air pressures where liquid water might pool in shadowed valleys. This isn't terraforming as flashy Hollywood makeovers. It's more like rewilding on a planetary scale, where each molecule of gas added is a vote for a future that hasn't arrived yet. And here's the twist: the slower the buildup, the more stable the result. Rushing could lead to runaway greenhouse effects or toxic atmospheric cocktails, turning Mars into a cautionary tale rather than a second home. The real test comes when biology enters the equation. Once pressures and temperatures edge into survivable ranges, extremophile microbes could be introduced to jumpstart soil chemistry, breaking down rocks into nutrients and exhaling trace oxygen as byproducts. These pioneers would work in slow motion. Lichen might take 50 years to spread across a single crater, algae a century to tint a shallow sea green. Entire human lifetimes could pass between milestones: the first rainfall, the first river that doesn't evaporate instantly, the first patches of grass surviving unprotected. This glacial pace forces a radical shift in perspective. Societies accustomed to quarterly earnings reports and 5-year plans would need to embrace projects where success is measured by grandchildren's grandchildren. What makes this timeline bearable is the incremental payoff. Early colonists might live in domed cities, but each generation would witness small victories: thicker skies, milder winters, perhaps even the first cloud scudding across a pinkish horizon. Robotics and AI would act as stewards across the centuries, maintaining systems when human attention spans falter. The real challenge isn't technological, it's psychological. Can we commit to a project with no immediate ROI, where the beneficiaries are people not yet born? History offers glimmers of hope. Medieval cathedrals took lifetimes to build, their architects knowing they'd never see the spires completed. The difference is scale. This isn't one building, but an entire world under construction, and that's where robotics becomes indispensable. While humans debate and dream across generations, machines would be the silent workhorses, autonomous bulldozers regolith, farming to darken surfaces for heat absorption, swarms of drones monitoring atmospheric chemistry, self-repairing solar panels powering it all under dusty skies. These aren't the humanoid robots of sci-fi. They'd be specialized, rugged, and above all, patient. A single terraforming drone might outlast a dozen human caretakers, its algorithms tweaked by remote teams light minutes away. The true legacy of early settlers might not be the changes they witness, but the robotic systems they leave behind: autonomous gardeners tending a world they'll never see bloom. The beauty of this generational approach is that it mirrors Earth's own history. Our planet didn't become habitable overnight. It took billions of years of volcanic outgassing, cyanobacteria exhaling oxygen, and ice ages sculpting the land. Magnetic terraforming condenses that timeline, but still respects the rhythm of planetary evolution. The key is recognizing that some processes can't be rushed, that soil needs time to become soil, and skies need epochs to turn blue. What we're really building isn't just a habitat, it's patience itself, woven into the DNA of a civilization learning to think in geological time. Up next, we'll explore how robotics could become the unsung heroes of this epoch, not just as tools, but as guardians of humanity's longest experiment. Because when you're reshaping a world, the machines you send today might still be working centuries after your name is forgotten. Robots could become the unsung architects of our interplanetary future, laboring in the relentless cold and radiation where no human could survive. Picture autonomous drones the size of trucks, crawling across Martian plains to deploy magnetic coil stations, their movements precise despite the planet's thin, dusty winds. These machines wouldn't just build, they'd adapt. Advanced AI would let them troubleshoot solar panel malfunctions or reroute around unexpected terrain, all without a single command from Earth. This isn't science fiction. Prototypes like NASA Mars rovers have already proven robots can operate for decades in brutal conditions. The leap to terraforming robots isn't about inventing new hardware, it's about scaling up autonomy to planetary engineering. Early missions would focus on infrastructure invisible from orbit. Swarms of excavator bots might tunnel into regolith to bury superconducting cables, shielding them from temperature swings. Others could construct sprawling solar farms or drill deep into ice caps, releasing trapped CO2 to thicken the atmosphere. The real game changer, self-replicating factories. Imagine a single lander unpacking itself to produce more robots from local metals, each new unit expanding the workforce exponentially. This concept, called von Neumann probes, turns one shipment into an army, transforming a dead world's raw materials into terraforming tools. The energy demands are staggering, but so were the pyramids, and those were built with Bronze Age tech. AI would serve as the nervous system of this operation. Unlike pre-programmed robots, learning algorithms could analyze atmospheric data in real time, adjusting gas mining rates or magnetic field strength to optimize growth. They'd prioritize tasks humans might overlook, like redirecting dust storms to darken surface ice, accelerating sublimation. Some models even suggest cooperative networks where robots communicate like a hive mind, sharing power and resources across thousands of kilometers. The goal isn't just efficiency, it's resilience. A single malfunctioning bot wouldn't doom the project, just as one dying cell doesn't kill an organism. Yet these machines face challenges no Earth-bound robot has endured. Martian dust clings like powdered glass, jamming joints and coating solar panels. Lunar regolith is worse. Its jagged particles could shred insulation over time. Solutions range from self-cleaning nanoscale surfaces to robots that maintain other robots, like a planetary immune system. Radiation poses another hurdle. Cosmic rays can flip AI memory bits, causing glitches. Redundant systems and radiation-hardened chips borrowed from spacecraft design could help, but the ultimate fix might lie in underground control centers, where humans or shielded supercomputers oversee surface operations. The timeline for robotic terraforming stretches far beyond human lifespans, raising philosophical questions. Should these machines carry cultural archives or DNA banks, preserving Earth's legacy in case civilization stumbles? Could they develop their own goals if left unsupervised for centuries? Science fiction warns of rogue AI, but the greater risk might be apathy, generations of humans losing interest in a project their great-grandparents began. That's why the most critical robots might not be builders, but storytellers, drones that beam back vivid holograms of progress, making a centuries-long transformation feel tangible to distant Earth-bound audiences. What makes this approach revolutionary is its patience. Robots don't rush. They can spend years perfecting a single crater's microclimate or waiting for comet ice to vaporize. Where humans see desolation, they see potential, one calibrated adjustment at a time. And when the first colonists finally arrive, they might find not a barren wasteland, but a world prepped for life by silent, steadfast guardians who never needed a day off. This seamless collaboration between machine and planet hints at a deeper truth. Terraforming isn't just about technology. It's about learning to work with a world's rhythms, whether through magnetic fields or autonomous miners. And as we'll soon see, those rhythms might already include life forms we've yet to recognize, alien organisms that challenge our very definition of a dead world. Magnetic fields might be the silent guardians of life across the cosmos, not just on Earth, but on any world where biology clings to existence. Imagine a microbe thriving deep in the cracks of a Martian rock, shielded from deadly radiation by nothing more than the planet's residual magnetism. Or organisms floating in the subsurface oceans of Europa, their survival tied to Jupiter's colossal magnetic embrace. These aren't just hypotheticals. On Earth, we've found extremophiles organisms that flourish in places once deemed uninhabitable, from nuclear reactor cores to acidic hot springs. If life exists elsewhere, it's likely playing by similar rules, using magnetic fields as an invisible lifeline against the chaos of space. Studying these Earth-bound extremophiles offers a blueprint for what alien life might endure. Take Deinococcus radiodurans, a bacterium nicknamed Conan the Bacterium, for its ability to survive radiation doses thousands of times stronger than what would kill a human. It doesn't just endure, it repairs its shattered DNA like a microscopic mechanic. Now picture a similar organism on a world like Mars, where surface radiation is a constant threat. Without a global magnetic field, such life would need extraordinary adaptations, perhaps biofilms that block ultraviolet rays or enzymes that neutralize radiation-induced toxins. Understanding these mechanisms wouldn't just satisfy curiosity, it could redefine our approach to terraforming. If microbes can survive in harsh conditions, could we engineer them to improve those conditions? Imagine seeding a planet with organisms that not only tolerate weak magnetism, but actively help stabilize an emerging atmosphere. The search for extraterrestrial life and the project of terraforming are two sides of the same coin. Both hinge on magnetism's role as a cosmic gatekeeper. When astronomers scan exoplanets for habitability, they prioritize worlds with potential magnetic fields, those that could deflect stellar winds and retain atmospheres. A planet without this shield might still harbor life, but it would be huddled in caves, ice sheets, or deep oceans, far from the sterilizing fury of its star. This changes how we design missions to Europa or Enceladus. Instead of scanning surfaces, we might drill through miles of ice, following magnetic anomalies to hidden biospheres. Yet the implications go deeper. If life elsewhere depends on magnetism, terraforming becomes more than an engineering challenge, it's an ethical dilemma. Would strengthening a planet's field to suit human needs disrupt native ecosystems? Could we accidentally smother alien life by making a world too habitable? These questions force us to confront a paradox. The same technology that lets us revive dead worlds might also erase the very life we're searching for. This tension between creation and preservation leads us to the next hurdle, one measured not in Teslas or microbes, but in dollars and cents. The economics of magnetic terraforming stretch budgets beyond earthly scales, demanding innovations as radical as the vision itself. How do you fund a project that spans centuries with costs rivaling the GDP of nations? The answer might lie in rewriting the rules of resource allocation and redefining what we consider worth the price. The price tag for terraforming a planet reads like something out of science fiction, trillions upon trillions of dollars stretched over centuries, dwarfing even history's most ambitious projects like the Apollo program or the International Space Station. But here's the twist: humanity has faced similarly impossible-seeming costs before. The construction of the Panama Canal, for instance, consumed nearly $350 million in early 20th century money, an amount so vast it nearly bankrupted a nation. Yet today, the canal generates billions annually in global trade. The lesson: mega projects often pay for themselves in ways that aren't immediately obvious. Terraforming could follow the same arc, transforming from a fiscal black hole into an engine of cosmic prosperity. Consider the resource calculus alone. A single asteroid like Psyche, orbiting our solar system, contains enough nickel and iron to glut Earth's markets for centuries. Mars boasts vast deposits of rare Earth metals beneath its rust-colored sands, while lunar helium-3 could fuel future fusion reactors. The catch is accessibility. Without a stable atmosphere and magnetic shield, mining these treasures remains prohibitively expensive. Terraforming changes the equation. A protected Mars with breathable air and liquid water wouldn't just be a colony. It'd be a factory, a research hub, and a launch pad for deeper space exploration, all rolled into one. The initial investment might stagger budgets, but the long-term payoff could rewrite human economics. Funding such ventures demands unprecedented collaboration. Picture a consortium where private entities like SpaceX handle hardware deployment while NASA and international partners manage scientific oversight, a model echoing the ISS but scaled to planetary dimensions. Add sovereign wealth funds from nations betting on off-world mining rights, and suddenly the financial architecture starts taking shape. There's even talk of terraforming bonds, long-term securities where payouts align with atmospheric milestones, like the first measurable ozone layer or stable rainfall. It's capitalism meets cosmic manifest destiny, with dividends measured in breathable air rather than quarterly profits. Yet idealism may prove just as crucial as economics. Climate change and nuclear brinkmanship have shown how fragile Earth's biosphere really is. For a fraction of global military spending roughly $2 trillion annually, we could bankroll magnetic field generators or atmospheric processors, buying humanity a second home before disaster strikes. The cost of not acting might ultimately be higher. After all, dinosaurs didn't have space programs, and look how that turned out. The real game changer. Self-amortizing technologies. Early-stage terraforming could focus on systems that pay their own way, like solar satellites beaming energy back to Earth, or bioengineered algae producing pharmaceuticals in Martian greenhouses. Each revenue stream would chip away at the debt while advancing the broader mission. It's the Industrial Revolution played out on interplanetary scales, where every watt of power and gram of biomass inches a dead world toward habitability. This leads us to the ultimate question: which worlds are even worth the effort? Not all planets are created equal when it comes to terraforming potential. Some might require too much energy to stabilize. Others could harbor hidden biospheres we'd risk destroying. The next chapter in this cosmic saga isn't just about engineering, it's about real estate. And the choices we make today will echo across millennia, determining whether humanity becomes a single planet species or the architects of a living galaxy. Mars may be the poster child for terraforming, but it's far from the only world where magnetism could rewrite the rules of habitability. The red planet's thin atmosphere and frozen water reserves make it a straightforward candidate, relatively speaking, but venture further into the solar system, and the challenges grow as strange as the landscapes themselves. Take Venus, Earth's twisted twin, shrouded in clouds of sulfuric acid with surface temperatures hot enough to melt lead. Its thick carbon dioxide atmosphere is actually too much of a good thing, a runaway greenhouse effect gone horribly wrong. Here, magnetic terraforming wouldn't focus on protecting an atmosphere, but on managing one. A carefully tuned artificial magnetosphere could deflect just enough solar radiation to cool the planet over centuries, while solar shades at Lagrange points might block sunlight to jumpstart the process. The goal wouldn't be to eliminate Venus's atmosphere, but to thin it enough for breathable air to exist at higher altitudes, where temperatures and pressures approach Earth-like conditions. Imagine floating cities in Venus's upper atmosphere, tethered to mountain peaks where the air is almost survivable, all made possible by magnetic fields regulating the solar energy that turned the planet into a hellscape. Then there are the ice moons Europa, Enceladus, Ganymede, where magnetic fields interact with subsurface oceans in ways that blur the line between geology and biology. Europa's global saltwater ocean, hidden beneath miles of ice, is kept liquid by tidal forces from Jupiter's gravity. But the Moon also sits within Jupiter's colossal magnetic field, which induces electrical currents in that salty ocean, potentially providing energy for exotic life forms. Terraforming such a world wouldn't mean melting the surface ice. That would take more energy than humanity has ever produced. Instead, we might use targeted magnetic fields to stabilize radiation belts, making the icy surface safer for research stations while leaving the subsurface ecosystem intact. The challenges multiply when dealing with tidal heating. Alter a moon's orbit slightly, and you risk freezing or boiling its hidden seas. This demands precision engineering where magnetism acts as a scalpel rather than a sledgehammer, fine-tuning environments without disrupting delicate alien biospheres we don't yet understand. Even Mercury, the scorched innermost planet, presents unexpected opportunities. Its lack of atmosphere and extreme temperature swings make it seem inhospitable, but Mercury boasts a surprising secret: a weak global magnetic field, likely generated by a partially molten core. This field is too feeble to retain an atmosphere under current conditions, but with careful manipulation, it could become the foundation for something greater. Solar mirrors in polar orbit could focus sunlight onto Mercury's icy poles, sublimating trapped water, while an enhanced magnetic field prevents rapid escape into space. The result might be a thin but stable exosphere, creating habitable zones in permanently shadowed craters where temperatures stay moderate. Unlike Mars or Venus, Mercury's terraforming would happen in isolated pockets rather than globally archipelagos of habitability in a sea of extremes. The diversity of these candidates reveals the true power of magnetic terraforming. It's not a one-size-fits-all solution, but a toolkit adaptable to radically different worlds. A Mars-style approach would fail catastrophically on Venus, just as Europa's ocean shielding would be irrelevant on Mercury. Each environment demands bespoke solutions, field strengths calibrated to atmospheric composition, orbital distances factored into solar wind exposure, even the rotation rate of the planet influencing how magnetic shields must be configured. Gas giants like Jupiter are likely forever beyond our reach, but their moons present tantalizing edge cases where magnetism could create habitable zones without full planetary transformation. This adaptability hints at an even grander possibility. Exoplanets orbiting red dwarfs, the most common stars in our galaxy, face brutal stellar winds due to their close orbits. Many may have had their atmospheres stripped away eons ago, but an artificial magnetosphere could theoretically resurrect such worlds, shielding them long enough for outgassing or comet deliveries to rebuild their air. The same principles tested in our solar system might one day apply to planets light years away, turning the galaxy's frozen or scorched orphans into new frontiers. Every world is a unique puzzle, and magnetism provides some of the most versatile pieces for putting those puzzles together. Yet solving the physics is only half the battle. The moment we begin reshaping other worlds, we trigger societal shifts that will echo through generations. Becoming multi-planetary doesn't just mean new homes, it means new cultures, new economies, and new definitions of what it means to be human. Societal norms wouldn't just evolve on new worlds, they'd fracture and reform in ways we can barely predict. Picture the first Martian colonists, a mix of scientists and survivalists, building domed cities under rust-colored skies. Within generations, their descendants might develop entirely new dialects, their speech shaped by the acoustics of pressurized habitats and the need for precise technical communication. Holidays could revolve around solar flare warnings or the anniversary of first touchdown, while Earth seasons become abstract concepts remembered only in history lessons. The very rhythm of life would change. Martian days are 39 minutes longer than Earth's, and years last nearly twice as long. Over centuries, these subtle differences could birth cultures as distinct from Earth as medieval Europe was from Imperial China. Politics would face unprecedented challenges when ballots cross interplanetary distances. Imagine a Martian governor waiting 20 minutes for each instruction from Earth, or lunar miners demanding independence from terrestrial corporations controlling their oxygen supply. The Outer Space Treaty of 1967 prohibits nations from claiming celestial bodies, but what happens when corporations or private settlements start wielding real power? We might see the first corporate city-states since the East India Company, complete with their own currencies and defense forces. And with resources like asteroid metals or Martian water up for grabs, conflicts could escalate beyond Earth's jurisdiction into uncharted legal territory. The phrase international law might need to become interplanetary law, with all the chaos and innovation that implies. Human psychology will undergo its own metamorphosis under alien skies. Studies of astronauts on the ISS show how prolonged confinement reshapes perception. Some report the overview effect, a profound shift in perspective from seeing Earth as fragile and borderless. Now amplify that by orders of magnitude. Children born on Mars will never feel real rain or breathe unfiltered air. Their concept of nature might center on hydroponic gardens and virtual forests. Some psychologists warn of solipsism syndrome, where colonists develop an intense inward focus from living in monotonous, enclosed environments. Others speculate about terra nostalgia, a debilitating longing for Earth's open spaces among off-world settlers. These aren't just medical concerns, they're cultural time bombs that could shape entire civilizations. The technological ripple effects could dwarf the Industrial Revolution. In a world where every breath is recycled and every calorie counts, waste becomes unthinkable luxury. Martian societies might pioneer closed-loop ecosystems generations before Earth adopts them, out of sheer necessity. Architecture would evolve for pressurized environments, favoring rounded corridors over sharp corners to minimize stress points. Even language could adapt. English might borrow heavily from Russian or Chinese depending on which nations dominate early settlements, creating linguistic hybrids as unique as Martian soil. And with lower gravity enabling feats of engineering impossible on Earth, off-world colonies could leapfrog terrestrial tech in surprising domains, from medicine to materials science. What makes this transition truly pivotal isn't the technology, it's the philosophical rupture. For the first time since Homo sapiens left Africa, humanity will split across environments so different they might as well be separate planets. This isn't like colonizing islands or continents. It's entering realms where nature itself follows alien rules. The values that emerge, perhaps prioritizing communal survival over individualism, or viewing technology as inherently life-giving rather than optional, could eventually feed back to Earth, reshaping terrestrial civilization in their image. Historians may one day mark this era not by wars or elections, but by the moment humanity ceased to be a single planet species and became something infinitely more adaptable. Yet for all its promise, this future remains precarious. The same technologies allowing us to reshape worlds could also doom them if misapplied, as we'll soon explore when examining the thin line between terraforming triumphs and ecological catastrophes. The dream of terraforming comes with a sobering reality. Not every attempt would end in success, and some failures could leave worlds worse than we found them. Picture a scenario where overzealous atmospheric pumping triggers a runaway greenhouse effect on Mars, turning its thin, cold air into an unbreathable carbon dioxide soup thicker than Venus's. Or imagine a miscalibrated magnetic field deflecting solar winds in unpredictable ways, creating radiation hotspots that fry sensitive equipment and any hopeful colonists. These aren't just hypothetical setbacks, they're potential extinction-level events for any fledgling biosphere we try to nurture. The stakes are astronomically high because, unlike Earth, where ecological disasters unfold over decades, a planetary-scale miscalculation could irreversibly alter a world within years. History offers cautionary tales. When scientists introduced cane toads to Australia in the 1930s to control pests, they couldn't foresee the ecological havoc that would follow. Now apply that same unpredictability to an entire planet. Introduce the wrong microbes to process Martian soil, and they might outcompete each other into oblivion, leaving behind a sterile wasteland. Pump too much greenhouse gas too quickly, and you could melt polar caps so rapidly that the resulting water vapor, a potent greenhouse gas itself, triggers unstoppable warming. Even magnetic shielding, for all its precision, carries risks. A field too strong might trap charged particles in dangerous radiation belts, while one too weak could let solar winds scuttle centuries of atmospheric buildup in a matter of months. Mitigating these risks demands more than just contingency plans. It requires a paradigm shift in how we approach planetary engineering. Think of it like building a bridge, except you're testing the design in hurricanes, earthquakes, and meteor showers simultaneously, with no room for a prototype. That's why rigorous simulations using quantum supercomputers would be non-negotiable, modeling every variable from atmospheric chemistry to magnetic turbulence across centuries. Some proposals even suggest starting with enclosed, test biomass, vast, sealed environments where we can trial terraforming techniques in controlled isolation before unleashing them globally. The goal isn't just to avoid catastrophe, but to engineer fail-safes like magnetic field generators that can be dialed down instantly, or atmospheric scrubbers that reverse greenhouse gas injections if thresholds are breached. Yet the greatest safeguard might lie in humility. Earth's biosphere wasn't built in a day. It evolved through trial and error across billions of years, with countless false starts and mass extinctions. Our attempts to fast-track that process on other worlds must respect the same principle: slow, incremental steps with constant course corrections. That means resisting the temptation to declare early successes like a marginally thicker atmosphere as victory, when the real work of stabilizing a planetary ecosystem could take millennia. This brings us to the ultimate question: how does magnetic terraforming stack up against other methods? From atmospheric factories to giant orbital mirrors, each approach has its own risks and rewards, but none offer the elegant, physics-based precision of harnessing a planet's electromagnetic heartbeat. Magnetic terraforming might be the most elegant solution we've explored, but it's far from the only tool in humanity's planetary engineering toolbox. Take atmospheric mirrors, gigantic orbital reflectors designed to focus sunlight onto a planet's surface, melting ice caps or warming frozen ground. These could jumpstart climate change on a world like Mars, where even a slight temperature increase might release trapped CO2 from polar ice, thickening the atmosphere naturally. The concept isn't new. In the 1970s, physicist Carl Sagan proposed darkening Martian polar caps with soot to absorb more sunlight. Today's versions are more sophisticated, think kilometer-wide Mylar sails positioned at Lagrange points, adjustable like cosmic dimmer switches. But mirrors alone have limits. Without a magnetic field to protect it, any new atmosphere would still bleed into space, leaving the project perpetually playing catch-up against solar winds. Then there's the brute force approach, greenhouse gas bombardment. By flooding a planet's air with supercharged warming agents like perfluorocarbons, which trap heat thousands of times more effectively than CO2, we could theoretically trigger rapid climate shifts. On paper, it's straightforward. In practice, the risks are staggering. Overdo it, and you risk creating a Venusian nightmare where temperatures spiral out of control. Underdo it, and the gases might dissipate before achieving meaningful change. Worse, many synthetic greenhouse agents are chemically inert, lingering for millennia without natural processes to break them down. Earth's own climate crisis shows how delicate these balances are. Scaling that uncertainty to a planetary level could backfire catastrophically. Biological solutions offer a gentler path. Genetically engineered microbes or lichens, tailored to survive harsh conditions, could slowly transform a planet's soil and air. Cyanobacteria, for instance, already produce oxygen as a byproduct of photosynthesis. Tweaked for Martian cold and radiation resistance, they might carpet the planet's surface, exhaling breathable air over centuries. The beauty of this method lies in its self-sufficiency. Once established, the organisms would require little maintenance. But biology is unpredictable. Introduce a microbe that outcompetes its peers or mutates unexpectedly, and you could end up with monocultures collapsing entire ecosystems before they've begun. And like mirrors, bioengineering alone can't solve atmospheric loss without magnetic shielding to hold the gains in place. What makes magnetism stand apart is its ability to address multiple problems at once. A robust field doesn't just protect an atmosphere, it reduces surface radiation, stabilizes climate systems, and even influences weather patterns. Compare that to mirrors, which only tackle temperature, or greenhouse gases, which solely manipulate air chemistry. It's the difference between patching a leaky boat and building a hull that doesn't leak in the first place. Yet the smartest approach might not be choosing one method over another, but blending them in stages. Early phases could use mirrors to warm polar regions, releasing trapped gases while magnetic coils are deployed in orbit. Once the field stabilizes, bioengineered organisms could be introduced to refine the atmosphere, with greenhouse gases acting as temporary boosters where needed. This hybrid strategy plays to each method's strengths while mitigating their weaknesses, like a medical team combining surgery, drugs, and physical therapy for a full recovery. The real challenge isn't technical, it's collaborative. Terraforming isn't a project any single nation or corporation can tackle alone. It demands global coordination, shared resources, and a vision stretching beyond political or generational boundaries. Which brings us to the next frontier, uniting humanity's fractured efforts into a cohesive plan for remaking worlds. Because if we can't cooperate on Earth, what hope do we have among the stars? International cooperation isn't just helpful for terraforming, it's non-negotiable. The sheer scale of reshaping a planet demands resources rivaling the combined budgets of Earth's wealthiest nations, alongside expertise spanning astrophysics, robotics, climate science, and geopolitical negotiation. Look at the International Space Station as a microcosm of what's possible. 15 nations collaborating for decades, sharing everything from solar panels to astronaut toothbrushes. Now amplify that to planetary engineering, where a single misaligned magnetic coil or overzealous atmospheric pump could destabilize centuries of progress. This isn't just about splitting costs, it's about distributing risk and responsibility across humanity, ensuring no one actor holds the fate of a world in its hands. Yet history warns us that shared projects don't always mean shared rewards. The Antarctic Treaty of 1959 suspended territorial claims on the icy continent, but off-world resources could ignite new conflicts. Picture a future where Mars's richest water deposits lie beneath land tended by robots from one nation, while another's orbital magnets shield the region. Who controls the air when the shield was built by one country, but the atmosphere thickened by others? Early frameworks like the Outer Space Treaty forbid national sovereignty in space, but they were drafted when lunar landings were the pinnacle of ambition. Terraforming operates on timelines and scales that render Cold War-era agreements quaint. The real test won't be technological, it'll be diplomatic. Can we draft interstellar zoning laws before the first territorial disputes arise? The stakes go beyond legal paperwork. Collaboration could forge unprecedented peace, binding nations together in a project so vast it makes Earth's squabbles seem trivial. A modern-day version of how the space race thawed Cold War tensions through shared achievement. Or it could fracture into a cosmic colonialism, where wealthy consortiums claim the most habitable zones while others remain tethered to an overcrowded Earth. Already, private companies scout asteroid mining rights like prospectors in a gold rush. Add terraforming to the mix, and the line between exploration and exploitation blurs. The danger isn't just conflict over territory, but over vision. Should Mars become a pristine laboratory, a second Earth, or an industrial hub? The answer depends on who you ask and whose checkbook is open. This tension between unity and self-interest plays out in smaller experiments today. The Square Kilometre Array, a global radio telescope project spanning Africa and Australia, shows how scientific megaprojects can empower local economies while advancing shared knowledge. Conversely, satellite internet constellations have sparked accusations of orbital hoarding, with corporations littering low Earth orbit with hardware that outnumbers natural stars in some night skies. Terraforming magnifies these dynamics to existential proportions. The very act of debating ownership of other worlds forces us to confront uncomfortable questions. Can humanity claim planets the way explorers once claimed continents? And if so, who gets to decide their future? Philosophically, terraforming holds up a mirror to our values. Are we stewards or conquerors? The answer may lie in recognizing that magnetism and atmospheres are just tools. The real transformation happens in how we choose to wield them together. A world rebuilt by many hands could become our greatest achievement or our most tragic oversight. The difference won't be written in soil or sky, but in the treaties we draft and the alliances we honor long after the first artificial auroras fade. Reshaping a world isn't just an engineering feat. It's a mirror held up to humanity's deepest beliefs about our place in the cosmos. For millennia, we've seen ourselves as subjects of nature's whims, struggling against storms and droughts. But terraforming flips that script, casting us as architects of entire biospheres. This shift forces uncomfortable questions. Do we have the right to remake worlds in our image? Indigenous cultures from the Amazon to Australia speak of sacred landscapes shaped by ancestral beings. What happens when humans assume that create a role on planets where no life existed before? The tension isn't just philosophical, it's practical. A single misstep could turn Mars into another Venus, proving our power to destroy extends beyond Earth. The theological dimensions run just as deep. Many faiths teach stewardship, the idea that humans are caretakers, not owners of creation. but terraforming demands active intervention rather than passive preservation. Some scholars compare it to the biblical concept of tikkun olam, repairing a broken world, while others warn of hubris reminiscent of the Tower of Babel. Even secular perspectives grapple with the paradox. Our survival may require planetary transformation, yet that very capability makes us uniquely dangerous. Astronomer Carl Sagan captured this duality when he opposed Mars terraforming in the 1990s, arguing we might destroy native microbial life. His ideological opponent, Christopher McKay, countered that bringing life to dead worlds could be humanity's highest calling. The debate remains unresolved because it's not about science, it's about identity. Ethical frameworks strain under these new horizons. Utilitarians might argue that creating trillions of future lives justifies altering a planet, while deep ecologists insist worlds have intrinsic value beyond human use. Consider the dilemma of panspermia deliberately seeding Mars with Earth microbes. If successful, these organisms could jumpstart ecosystems, but they might also obliterate potential alien life we haven't detected yet. It's the trolley problem scaled to planetary proportions. Is actively creating life elsewhere worth the risk of erasing what might already exist? Legal scholar Charles Cockell proposes planetary parks, wilderness preserves where no terraforming occurs, as a compromise between expansion and conservation. Yet on airless worlds, even preservation requires active maintenance, blurring the line between caretaking and control. What makes these questions urgent is their timeline. Unlike climate change, where impacts unfold over decades, terraforming decisions could lock in consequences for millennia. Future generations won't just inherit our technologies, they'll inherit the philosophical baggage of choices we make today. If we declare Mars a human colony, do its descendants owe allegiance to Earth? Cultures born under domed cities might develop values unrecognizable to their terrestrial ancestors, seeing planetary engineering not as extraordinary but as birthright. Historians note how the American frontier shaped democratic ideals. Off-world societies could undergo similar transformations, with magnetism and atmospheric processors replacing covered wagons and gold rushes as catalysts for change. The most profound implication might be cosmological. For 4 billion years, life on Earth was shaped by its environment. Terraforming reverses that relationship, making environments servants to biology. If intelligence truly is nature's way of understanding itself, then reshaping planets could be the universe's next evolutionary step, a transition from passive adaptation to active co-creation. Or it could be the ultimate act of arrogance, a toddler given the keys to a starship. The answer won't come from equations or engineering schematics, but from the stories we tell ourselves about what it means to be alive in a vast, silent cosmos. Speculation about terraforming's endpoint leads to staggering possibilities: worlds where cities bloom under manufactured skies, where children born under alien suns know Earth only as a mythic homeland. But before we reach that future, we must navigate the present's thorniest question, not whether we can reshape worlds, but whether we're wise enough to deserve the privilege. The technology may be ready within centuries, but the maturity to wield it, that timeline remains uncertain. Centuries from now, the barren wastelands we see today, Mars's rust-colored deserts, Venus's scorching plains, could be unrecognizable. Picture cities of crystalline domes stretching across valley networks carved by ancient rivers, their streets buzzing with a blend of human settlers and AI stewards. These worlds wouldn't just be outposts, they'd be civilizations unto themselves, shaped by the unique challenges of their environments. A child born on Mars might grow up with a spine elongated by lower gravity, their lungs adapted to thinner air, their culture woven from stories of the Great Thaw, the era when magnetic coils first sparked auroras over their ancestors' biodomes. This isn't just survival, it's speciation in real time, humanity branching into new forms as surely as life once crawled from Earth's oceans onto land. The real transformation lies in how these societies evolve beyond Earth's shadow. Freed from terrestrial politics and resource constraints, Martian or Europa colonies could pioneer social models as radical as their technologies. Imagine a culture where water is so precious that waste is unthinkable, giving rise to economies based on recycling efficiency rather than consumption. Or a society that treats energy as a communal right, with fusion reactors governed by algorithms ensuring equitable distribution. These aren't utopian fantasies, they're practical adaptations to worlds where every joule and milliliter must be accounted for. Over generations, such values could harden into traditions, making Earth's excesses seem as foreign as feudalism. Technological divergence would be equally profound. Mars's low gravity and abundant sunlight might make space elevators feasible, turning the planet into a gateway for asteroid mining. Venus's upper atmosphere, with its Earth-like pressure and temperature, could host floating laboratories where scientists manipulate supercritical fluids impossible to study on Earth. Each world's unique conditions would breed specialized innovations, like Europa's subsurface drilling bots or Mercury's sun-tapping energy grids. The galactic civilization of the future won't be a monoculture, it'll be a tapestry of interdependent specialties, each thread strengthened by its distinct origin. Yet this vision hinges on breakthroughs happening now. Every superconducting coil tested in orbit, every extremophile microbe engineered for alien soil, is a stitch in that tapestry. The theorists debating magnetic field geometries or atmospheric chemistry today are the unsung architects of tomorrow's empires. Their work echoes the Renaissance astronomers who mapped the heavens without dreaming their charts would one day guide starships. The difference is scale. Where Copernicus speculated about planets, we're preparing to reshape them. So where does that leave us? The key takeaway isn't just the physics of magnetism or the engineering of atmospheres. It's the audacity to think in cosmic time. Terraforming isn't a project for a lifetime or even a century. It's a covenant between generations, a promise that the choices we make today will echo in the voices of descendants who have never seen Earth's sky. They might call their home New Eden or Olympus, but its foundation will be the theories we test, the risks we mitigate, and the humility we carry into this grandest of experiments. The future of life among the stars begins not with a bang, but with a whisper, the quiet hum of a magnetic field waking a dead world to life.